linear algebra in 10 minutes. Let's go. Linear algebra is an incredibly useful concept. From data science to differential equations, we use it everywhere. And when we can represent problems through the lens of linear algebra, we can turn unsolvable problems into solvable ones. Concepts. First, we have fields. Fields are basically spaces with one element, which are scalars or numbers, and they have two operations, addition and multiplication. If you could prove that they're closed under their properties, you can effectively prove that they are a valid field. Vector spaces. Think of vector spaces to now have two elements and two operations. We have the same scalars, but we also have vectors. Vectors are of the form 1, 1, for example. But they could have an infinite amount of dimensions. We also have them being closed under addition and scalar multiplication. Next is a vector subspace. All vector subspaces are valid vector spaces. The one additional thing you need to prove for a vector subspace is that it includes the zero vector. So if we show that a vector subspace has a zero vector, it's closed under addition and scalar multiplication, these are basically good enough to solve any proof problem for a proof class, which asks you whether something is a valid vector subspace. Next, we have the concept of linear independence and a span, right? Linear independence is basically saying when we have a set of vectors, say x1 to xn, when we add coefficients in front of them and find their linear combination and set it to 0, the only valid coefficients that should send this to 0 should be all zeros, right? And this basically says that your set of vectors are linearly independent and not one vector can influence another vector, or we can obtain another vector from the combination of a few vectors. Span is basically how much of a vector space we can reach. A very easy example is the R squared space, right? The next topic will tie in very well with this, a basis. When we prove both linear independence and span, we have officially proven that something is a basis for a vector space. Going back to this R squared example, the standard basis for R squared is 1, 0, 0, 1, because using these vectors, which are linearly independent, we can basically find any vector in the R squared space, which is incredible. But this is not the only basis. This is just the standard basis because it's the most frequently used. It's the simplest looking basis. Next, we have linear maps. Now that we know what vector spaces are, we can see one vector space be transformed into another vector space. For instance, an R squared to R squared transformation. An example of this would be a linear map that projects every vector in the R squared space onto the x-axis. Just an example of a linear map. These specifically, where it maps from the same dimension to the same dimension, is called an endomorphism. But it's not necessarily the case that it always has to happen this way. We could also have maps from R3 to R2, right? There's a very useful theorem in linear maps called isomorphism. So suppose that we have a map or a vector space that is P1 of x, meaning it accepts 1 and x in any combination. It could be like 3x plus 1 is a valid P1 of x space, a vector in that space. Another way to represent P1 of x would be to represent it as R squared. where the value up top could be referencing the 1's position, and the value in the bottom could be referencing the x's position. And now we have a different representation of the P1 of x space, and we could show basically any vector in that space as an R squared vector. We also have this thing called a general linear group. This is just a definition that would be useful to remember in a linear algebra class. It's just a set of all invertible n by n matrices in F. Example would be GL of 2 in R. So in the real space, all 2 by 2 invertible matrices, where an example could be 2, 1, 0, 3. And if you don't remember how to invert a matrix, it is just following 1 over AD minus BC, which is the determinant, times 3 to negative 1, negative 0. These values are both negative. These values are swapped. That's for a 2 by 2 matrix. Next, we have solving equations of the form AX equals B. If we have an example matrix and we have some x1 and x2 that solves this, right? We can then expand out this equation by multiplying the rows with the columns. X1 plus 2x2 would give us 5. 3x1 plus 4x2 would give us 11. For larger matrices, however, we can use elementary row operations, which consist of swapping 2 rows. It consists of scaling 1 row and then adding it to another row. And it also consists of scaling, which I talked about. And that would simplify it much more to the point where we can form an upper triangular matrix, which is of the form all zeros below the top triangle, and then the top triangle would have values, right? And once we find that, it's very easy to find the values for the x's in the pivot positions. There's 2 other ways to solve AX equals B form problems, which is LU and LDU decomp, which for much larger values of n are actually faster because they use fewer operations. So in the long run, it is very beneficial to learn these as concepts. Next, we have the most important concept in all of linear algebra, eigenvalues and vectors. Eigenvalues basically are of the form lambda and given a vector, for example, is found by finding the determinant of A minus lambda times the identity matrix equals to 0. The relevance of eigenvectors is that they're basically the special vectors that when a linear map is used or a vector space is transformed to another vector space, these vectors are only ever scaled. They're not actually transformed out of that specific direction. Suppose this is a vector. An eigenvector can only ever be scaled this way or that way and never be transformed. And this has a lot of utility to find diagonal matrices, for instance, which are incredibly useful. What are diagonal matrices? A matrix is diagonalizable if it is of the form PD P inverse. Again, to find a diagonal matrix, you first have to find the eigenvalues. I can go ahead and find the eigenvalues for this right here. When I take A minus lambda I, this would be my resulting matrix. And now taking the determinant of that, I will get 4 minus lambda times 3 minus lambda minus 2 equals 0. I'd get lambda squared minus 7 lambda plus 10 equals 0. And thereby, I would get lambda equals 5 or 2. Right? Now, I can use these to find the eigenvectors by substituting it back into a minus lambda I, where you get negative 1, 1, 2, negative 2, and then a minus 2I would be 2, 1, 2, 1, right? You find the kernel of both of these. The kernel is what sends a particular matrix to 0. In this case, the kernel would be 1, 1. When I do 1 times x1 plus 1, a negative 1 times x1, I get 0. Same here. X2. And for this case, it would be 1, negative 2. And as you can see, similar to the first matrix, it will send everything to 0 when we sum it together using those specific values. And these are our eigenvectors, right? Now, basically, our diagonalizable form, which we want to get our matrix to, would be our P matrix would be our eigenvectors as columns, right? So 1, 1, and 1 minus 2. And then P inverse could be found, and D is basically our eigenvalues 5 and zeros in these diagonals and 2. So we've officially found our diagonal matrix for matrix A, and this matrix is super useful because eigenvalues from this matrix could be found immediately. It has several applications and makes calculation way easier. So hopefully this was a useful enough video covering all the concepts of linear algebra, and thank you all for watching, and hopefully you have a good day.